Okay, welcome to the first lesson of Chapter 4. We'll be going over angles and their measures. Most of this will probably be review for you, so I'll try to go through it quickly, but also thoroughly in case you don't remember it. We'll start off just with what measures of angles are. So first one we have here is degrees. Degrees is basically just an angular measure. Degrees come from base 60 counting, which actually happened way back in like Mesopotamia times, which is fascinating, I know. They like the number 60 because it's very evenly divisible by a lot of numbers. And so they tried to do everything as base 60. That's why time is based out of base 60 as well. So basically we have this very specific thing here, degrees, minutes, seconds. Each degree is subdivided into 60 minutes. Each minute is subdivided into 60 seconds. So you can kind of think of degrees like hours, and then you have hours, minutes, and seconds. So we'll get into a little example here of how we would convert this to degrees, minutes, seconds. So I start off with, I already have 37 degrees. So 37 degrees is what I'm going to start off with. That is a really thick marker, so let's tone that down a bit. What I'm going to do next is take this decimal part. So I'm going to do 0.425, and I'm going to multiply that by 60 to turn the 0.425 into how many minutes that would be. And that gave me 25.5 minutes. And we use this little tick mark there to represent minutes. Now what I'm going to do is take the decimal here, 0.5, and I'm going to multiply it by 60 again to turn this into seconds, which uses two little tick marks. So to write 37.425 degrees in DMS, we write 37 degrees, 25 minutes, and 30 seconds. This is really useful in navigation because we can be very, very specific with where we want to locate something. If we want to work backwards from this, we essentially just convert the seconds into minutes and then minutes into hours. So I'm going to first take this 36, I'm going to divide it by 60. That will give me the 42 degrees, 24.6 minutes then. So 36 divided by 60 is 0.6. Now I'm going to take 24.6 and divide it by 60. And that is going to give me 42.41 degrees when I add that to the original 42. And there you have it. That's the basics of DMS. Moving on, we introduce radians. So radians are just a different type of way to measure how big an angle is. And we like radians because they're what we call unit neutral. They actually don't hold on to their own unit, whereas degrees would hold on to degrees. Radians don't. So we have the definition of what a radian is. It says the central angle of a circle has a measure of 1 radian. So this part right here has a measure of 1 radian. If it intercepts an arc with the same length as the radius. Okay? So what that means is, here's my radius on either side. It means that this length right here is also equal to r. And that's what the definition of a radius is. Oh, sorry, a radian. I should edit that out and put it in the bloopers, right? I'm not going to, though. All right, so we're going to do an example of how we might use a question that involves this actual definition. So I have here the length of an arc intercepted by a central angle of 1/2 radian in a circle of a radius 5 circles. So that's what we're trying to find the length of the arc. So if I kind of just draw what this arc might look like, okay, so this is what I'm trying to find. I have a 1/2 radian angle measurement, and I have a radius of 5. Okay, so if I take this 1/2 radian and I duplicate it over here, so here's another 1/2 radian. Okay, this is going to be the same measure, and this is 5. And what I have now is a measurement that is 1 radian across. So from here to here is 1 radian. And according to the definition right above, it says that the arc length that's associated with 1 radian is equal to the radius. So in this case, 5. So my little red x plus my little green x has to equal 5. So 2 x's has to equal 5, so x is going to equal 5 over 2, or 2.5 inches. Okay? So the length of the arc that intercepts this particular half radian angle is 2.5 inches. Fascinating, right? Sometimes it's nice to be able to convert back and forth between radian and degrees, so we have this these little patterns here. If we're going from radians to degrees, we're going to multiply by 180 degrees divided by pi radians. Okay? And that works because pi radians is equal to 180 degrees. So those are equal measurements, kind of like 1 foot is equal to 12 inches. So they have different units, but they're equal. So same idea. And then if we're going from degrees to radians, that's what's over here, we do pi radians over 180 degrees. And kind of explain why that works in these two examples real quick. So if I have, how many radians are in 45 degrees? What I want to do is cancel out the units of the degrees and introduce radians. So I'm going to multiply this by pi radians and divide by 180 degrees. Because what will happen is my units of degrees cancel. And so what I'm left with now is 45 divided by 180. So pretty sure that 45 goes in 184 times, and I'm left with pi over 4 radians. So 45 degrees is equal to pi over 4 radians. If I'm going about this the other way, I have pi over 3 radians. I want to cancel out the units of radians. So I'm going to do 180 degrees on top divided by pi radians, because this allows the radian measurement to be canceled, because it's on top and bottom. I'm also lucky enough that the pi's cancel, and I have 180 and 3, so I'm left with 60. So pi over 3 radians is the same as 60 degrees. Not that bad, right? It's kind of annoying to use the radian definition of an arc length, so we came up with a little easier formula. And it's essentially that we're taking the percent of a circle and then we're multiplying it by the perimeter of that circle. Okay, so this first part here we have theta divided by 2 pi, so this is if we're in radians. That theta is going to be the certain angle we're looking for to give us the measure of our arc, out of 2 pi being the full time around a circle. So we do theta over 2 pi, it's percent of the circle, times 2 pi r, which is the perimeter, and that gives us the arc length. The exact same thing happens if theta is in degrees. We just use 360 instead of 2 pi. So here we have an example of one. The perimeter of a 10-degree sector cut from a circular disc of radius 11 inches. So we want to find the perimeter. So here I have 10 degrees, and here is 11 inches, and I'm trying to find the entire perimeter, not just this measurement, so the entire perimeter of this part. So first, I need to figure out what the length of this arc is. So I know that it's 10 degrees over 360 degrees. The units of degrees will cancel out here, times 2 pi 11. Okay, so we use our calculators to help us simplify this down. I believe we get 11 pi over 18, which we can approximate as 1.9199 inches. So that's only the length of this arc right over here. If we want the perimeter, we need to include all the sides. Okay, so the entire perimeter is going to be 11 plus the 11 pi over 18. Okay, which we would simplify and just say 22 plus 11 pi over 18. And if we were using our calculator, we would say that it is 23.9199 inches. It's the entire perimeter. So either one of these works. Another example of this, we have a 5 pi over 9 radian arc of a circle has a length of 7 centimeters. Okay, so here's my angle measurement, 5 pi over 9. The arc itself has a length of 7. I'm trying to decide what the radius must be. Okay, so setting up my formula, I have the part of the circle out of the entire circle times the radius, which I don't know what r is yet. I know that this has to equal 7. So luckily some things cancel out here. The 2 pi's cancel, so I'm really left with 5 pi r over 9 equals 7. And now I just need to get r by itself. So I'll multiply by 9 and divide by 5 pi. So r is going to equal 63 over 5 pi, which is approximately 4.0107, I think, centimeters. And here's our answer. Not so bad, right? Okay, so here we're getting to the real heart of this entire chapter. It's based off of trigonometry, and we're finally introducing that. So we had to figure out what angles were. Now we can use trigonometry. So trigonometry is the study of triangles. And we start off with reminding you what similarity is. Okay, so similarity in terms of triangles is just when all three angles are the same. Okay, side lengths can be different lengths, but they're similar if the angles are the same. And that is the basis for all right triangle trig. And since we know we're dealing with right triangles right now, we really only need to know that one of the other two remaining angles is the same in our two different triangles that we might work with, because we automatically know the third one then, because we know that triangles add up to 180 degrees. Okay? So we really need to know this one angle theta, and that lets us figure out everything we need to know. And theta, for now, will be measured in terms of 0 degrees to 90 degrees, or 0 radians to pi over 2 radians. Because it's in a right triangle, we can't have an obtuse angle. Okay? And if we connect back to geometry, the angle, okay, is really defined as two rays. So I'm going to draw two rays in our little picture over here. I'm going to have these two. And I purposely did this so that I have a side length of 3, 4, and 5 if I kind of put a line in between these two rays. Okay? And here would be the theta we're talking about, and this is a right angle. We typically draw these in what we call the standard position, and standard position is in the first quadrant, just like I just drew it. If I come down to my trig functions, here's your SOHCAHTOA that you're used to. In terms of our triangle, if I let this be theta, okay, the side opposite of that we label as opposite. Here's 90. The side that's opposite of 90 is going to be the hypotenuse. And then the side that's kind of right next to the angle but not the hypotenuse is called the adjacent side. In terms of our example up above, we had this side labeled as 3, this was 4, and then this is 5. So using the trig functions, I can say sine of theta, whatever that theta is, I know that it's going to equal 3 over 5, so the opposite over the hypotenuse. Cosine of whatever that angle is going to be 4/5. Tangent is going to be 3/4. Notice that that's really the top part of sine and cosine, and that comes together to make tangent. So that's something that we'll use as we want to develop some shortcuts. For cosecant, secant, and tangent, they're really just the reciprocals of sine, cosine, and tangent. So I can take the answers I just found and kind of flip them upside down. Okay? And there you have it. Doing an example with these, okay, we have find the height of a building. So here we have a pretty little building. It's got some doors and some windows and stuff. It's looking real cute. Maybe it has a nice little chimney up here. Okay. We're trying to find the height of this. We are standing 340 feet away. We have angle of elevation, which remember comes from the ground up, 65 degrees. Okay. Versus our angle of depression would be coming from some horizontal going down. But those are always identical. You should remember that angle of elevation and angle of depression are actually the exact same number. All right, so goal here is to find h. If I'm looking at this 65 and I let that be my main angle, I have side h is opposite it, and I also know side that's adjacent to it. So I'm going to use tangent to solve this. So tangent of 65 degrees is equal to h divided by 340. Just get h by itself by multiplying the 340 to the other side. Notice I wrote it in front. That's so I don't accidentally put 340 inside of the tangent function. From here, I'm just going to use my calculator, and I'll get that h is approximately 729 feet. So, I don't know. There's probably a couple more windows in this drawing. Not sure. Okay, so here we have our special right triangles. These are your best friend. You must know these things inside and out. We start off with a 45, 45, 90. That's one of the two main types of triangles we work with. And in this, there are a couple different ways that you might label it. I think the way that a a lot of you guys like to label them is, I think, maybe 1, 1, and then root 2. Okay, if you don't like that way, there's other ways. So, like, I don't know, my teachers were weird and they made me memorize it like this, root 2 over 2, root 2 over 2, and 1, which is really the same exact thing. But really, it's any sort of combination of this. Okay, so we could make the side lengths like be 5, 5, and then it would be 5 root 2. Anything, but doesn't really matter. If you come over here and we evaluate, we'll use the green ones here. So let me erase my ones that my teachers made me do. Okay, so if I let this one be theta, it doesn't really matter because they're both the same exact angle. I'm going to have 1 over root 2. Okay, and you have to rationalize these ones. This is the only time you have to rationalize for me, pretty much. We do cosine of this. It's also 1 over root 2, so that's the square root of 2 over 2. Tangent is 1 over 1, so that's just 1. Cosecant, secant, and tangent, they're kind of like the sine, cosine, and tangent, except they're flipped upside down. So if I take the original one of sine here and flip it upside down, I'm just going to get the square root of 2 over 1. Same thing with secant. If I take cosine and flip it, the original part before I rationalized it, I get square root of 2. Tangent, if I do 1 over 1 and I turn that upside down, I still get 1 over 1. There you have it. You need to know this and you should recognize sine of 45 is square root of 2 over 2. Cosine of 45, square root of 2 over 2. Tangent of 1 is, tangent of 45 is 1. You gotta know those. If we're doing this with a focus on 30, so here I have 30, 60, and 90. So 30 is going to be the theta that I'm talking about in my problem. And there are a couple different ways that you might have learned to write this one as well. This is the main way that people use. So if I do sine, my opposite side is 1, my hypotenuse is 2. Cosine of 30 is going to be the square root of 3 over 2. And tangent is going to be 1 over the square root of 3, which becomes the square root of 3 over 3. For cosecant, secant, and tangent, same idea. I'm going to take the answers I have over here, turn them upside down. So 1 over 2 becomes 2 over 1. This becomes 2 over root 3, which I have to rationalize. Tangent, I'm going to use the original one, and I'll just get root 3. And we're done. You got to know these ones. Okay? Mainly sine, cosine, and tangent. You can get away without knowing the cosecant, secant, tangent if you know sine, cosine, tangent. Okay, here we have a focus on 60, so I just kind of turned my triangle so that it was a little easier for me to see what was going on. Okay, this is the angle I'm working from. So if I do sine of this, it's going to be the square root of 3 over 2. Cosine is going to be 1 over 2. Tangent is going to be the square root of 3 over 1. Same idea for cosecant, secant, tangent. Turn them upside down, so I get 2 over root 3, which I rationalize to be 2 root 3 over 3. Secant is now 2, and hey, that's a typo. That should say cotangent. Is it like that on the other one? Awkward. Cotangent. Was it like it on all of them? Why didn't anyone tell me earlier? You let me go through the entire video like that. Embarrassing. That's what copy and paste gets you. Alright, so anyway, cotangent, it's going to be 1 over root 3, which I'll rationalize to be the square root of 3 over 3. You might notice a connection between sine of 30 and cosine of 60, and some of the other ones. We'll explore that a little bit later on. Okay, here's some Q&A for you. These are common errors that people mess up. Number one thing that they do is the wrong mode. Okay, in your calculator you have radian and degree mode. You got to make sure you're in the right one. Here, this is just notation. If I have sine theta squared, like it's written over here, that's identical to me saying sine squared theta. It's just a shorthand notation, so we don't need the parentheses. Here, 1 divided by sine theta is equal to cosecant theta, and we can't write that as sine to the negative 1 because this actually means inverse sine, which we'll learn in a couple days. Ooh, that's not how you spell sine. Rookie mistake. Makes a fat marker now. That's what I get. Okay? And here, you want to be really careful, especially if you're typing this in your calculator. Sine of 30 plus 2, the calculator is going to read it like that and do sine of 32. So if you really want to do sine of 30 and then add 2 to that, you need to make sure you close the parentheses. So those are just some common mistakes that people might make, something to be careful about. And there you have it. The rest is going to be practice. We'll go over stuff in class. And hopefully you like this kind of new model. And we'll see if we want to keep going with it. Okay. Peace out, Cub Scouts.